Hello, my name is Oswaldo Andrés-Martínez. I'm a postdoctoral associate. This work is about an optimal design of a novel ammonia synthesis process for solar thermochemical energy storage. This work is within the context of concentrating solar power, or CSP, which plays a critical role in the transition to a net zero carbon economy. This technology uses mirrors to focus sunlight onto a receiver, heating a fluid that can be used to produce heat and electricity. The levelized cost of electricity of CSP has dropped by more than 50% in the past decade, and it's expected to keep going down. Since solar energy is intermittent, so this technology incorporates thermal energy storage, and this makes it a reliable source of renewable energy that can help balance energy supply with demand. And the high temperature heat can be used in other sectors like cement, steel, and chemical production. So one important aspect of this technology is the use of thermal energy storage. And this is the focus of this work. This figure illustrates an ammonia-based solar thermochemical energy storage concept that was first proposed in the mid-1970s at the Australian National University. It consists of two cycles. Here on the left we have the solar receiver cycle, also known as charging loop. Here solar energy is used to dissociate ammonia into nitrogen and hydrogen. This reaction is endothermic, and therefore it absorbs solar energy. This gas is stored, and when the energy stored here is required, then we recover that energy using the heat recovery cycle, also known as discharging loop. Here this gas is used to synthesize ammonia, and since this reaction is highly exothermic, it releases heat that is used to increase the temperature of a fluid like steam or CO2 that can be used for power generation. This technology has some advantages. For example, it uses a carbon-free reversible chemical reaction. It exhibits minimal energy losses during storage operations, and it can benefit from a mature infrastructure available given by the Haber-Bosch process that has been used to produce ammonia for over a century. However, efforts are needed to improve the efficiency of this technology so that it becomes technically and economically competitive. The focus of this work is on the heat recovery cycle, specifically the ammonia synthesis process, without including the power generation section. This figure illustrates the process flow diagram of an absorbent enhanced ammonia synthesis process for heat recovery. It's very similar to a Haber-Bosch process. Here, within the underground storage, we have a stoichiometric mixture of nitrogen and hydrogen that was previously produced in the solar receiver cycle, and this gas is compressed and preheated as it flows through this loop. Once it reaches this heat recovery reactor, it's put into contact with catalyst, so it reacts to produce ammonia, releasing heat, and that heat is used to increase the temperature of a stream of supercritical steam. This autothermal reactor also contains some catalyst, and ammonia is synthesized, releasing heat that is used to preheat the feed gas. The conversion in these reactors is relatively low, therefore the effluents contain nitrogen, hydrogen, and ammonia. And it's very important to remove as much ammonia as possible so that we can recycle the unreacted nitrogen and hydrogen. And this is achieved using absorption. This absorber bed contains an absorber material that removes ammonia, releasing heat. Therefore, we call it a heat exchanging absorber. Once this bed is saturated, then we can recover ammonia as liquid. And this liquid ammonia can be stored separately, or it can also share the same container with the gas. Okay, some advantages of using ammonia absorption. First, ammonia is selectively absorbed, and this enhances the conversion in the reactors. Here we are avoiding the use of condensation, which is usually energy intensive, and the heat of absorption can be used for preheating. So both ammonia synthesis and ammonia absorption are exothermic reactions, and that offers the opportunity for efficient heat integration, and that's what we are trying to accomplish here. The problem statement can consists of three questions that we are addressing here in this work. First, what is the optimal size of each process unit? The length and the diameter of each reactor and the absorber, the heat transfer area of the heat exchangers, and so on and so forth. Second, what are the optimal operating conditions? For example, the mass flow rate here in the loop, the split fraction here, the temperatures of each stream, the composition, and third, how much stored gas is required for a given thermal output. For example, if we fix the mass flow rate of steam and the inlet and outlet temperatures, that produces a certain amount of thermal heat, we would like to know how much gas we need to store here, or how much gas we need to produce in the solar receiver. And the approach to answer these questions consists of two steps. First, the rigorous modeling of each process unit, and second, the simultaneous optimization of sizes and operating conditions associated with each process unit. So the first step is the modeling of each process unit. We are here considering a triple concentric tube arrangement for the reactors and the absorber, and this configuration is basically a vessel with two tubes inside. This creates two annular spaces. Here in the outer annulus we place the solid material like catalyst or absorbent. So the gas flowing in this outer annulus reacts, releasing heat, and that heat is transferred to the gas flowing in the inner annulus. The reactors, the autothermal reactor and the heat recovery reactor, operate in a steady state way. Therefore, they are described using a 1D flow reactor model that includes energy, mass, and momentum balances across the length. The kinetic model was taken from the literature, and we are considering an iron-based catalyst. This gives rise to a system of differential algebraic equations. On the other hand, the absorber never reaches a steady state, so it's a transient process, and therefore it's described using a temporal space flow model that includes energy, mass, momentum balances. To describe the mass transfer, we used a kinetic model, an empirical kinetic model taken from the literature, with some experimental information provided by some collaborators in this project. The absorbent material considered is magnesium chloride, and this gives rise to a system of partial differential equations. So here we face a challenge. We need to integrate these two mathematical descriptions in order to optimize the design of the reactors and the absorber. However, the system describing the reactors describes steady state processes, whereas this PD system describes a transient process. So here we propose a strategy called nested optimization simulation that separates the steady state process units from the transient absorption. So given some information like the power requirement or the amount of thermal output that we would like to produce in the heat recovery reactor, some properties associated with the absorbent, the catalyst, and the gas, some parameters describing the process units and the costs, we solve this optimization problem, which is a nonlinear programming formulation. This problem has this form. It minimizes the total capital cost of all process units, which is a function of the operating conditions and the size, subject to the model of the steady-state process units, the reactors, the heat exchanger, the compressor, the underground storage. And the codes published by the American Society of Mechanical Engineers, these codes are used to take into account the effect of pressure and temperature on the thickness of each process unit, because this thickness also has a strong influence on the cost. We also include some design and operating constraints. For example, the steam has to be heated from, let's say, 350 to 650. Another constraint is that the temperature inside each reactor should not go beyond a certain value that could compromise the performance of the catalyst. So once we solve this optimization problem, we obtain an optimal design, including an estimate of the absorber length. And then with this length and the rigorous model of the absorber, we simulate the absorption process and to see if this length is enough to remove enough ammonia. If it's not enough, this information is used to update the optimization problem. We solve it again and we obtain a new estimate of the absorber length. And again, we simulate the absorber to verify if this length is enough. And we repeat this process until the optimal length obtained here is enough to remove the amount of ammonia we need to remove. Then we obtain the optimal operating conditions, including pressure, temperatures, flow rates, and the optimal size of each process unit. And with this information, we can calculate some metrics like the levelized cost of heat and the efficiency of this design. This figure illustrates the optimal solution, the design of each process unit, and the operating conditions. Here you can see in blue the size of each process unit, and in red the operating conditions. Here in the heat recovery reactor, we are increasing the temperature of a stream of supercritical steam from 350 to 650. And this produces a thermal output of 18.43 megawatt thermo. And to produce that thermal output, we need to store 227 tons of gas at 217 bar. and we need to compress this gas to 260 so that we can produce enough ammonia that releases the necessary heat to produce this thermal output. The levelized cost of heat of this optimal design is 1.22 cents per kilowatt hour thermo. I found in the literature some reference costs associated with technologies based on sensible heat, and they report a range from 2.2 to 9.4 cents per kilowatt hour. So this gives us an idea of how good our levelized cost is. The discharging efficiency of this optimal design is 94%, which is good, and the exergetic efficiency is 29%. So here we have an opportunity to improve this exergetic efficiency. We can take a look at what's going on inside each process unit. For example, in the autothermal reactor, we can see here on the left the temperature profiles. We can see that the maximum temperature reached inside this reactor is 800 C, which is the upper limit imposed in the optimization problem. On the right, you can see the mass fraction profiles across the reactor. Similarly, for the heat recovery reactor, we have the temperature profiles here on the left. Again, the maximum temperature is 800 C. And on the right, you can see the mass fraction profiles. In the case of the absorber, since it's described with a temporal spatial model, we obtain three-dimensional plots. Here on the left, we can see the temperature profiles. The temperature inside the outer annulus, where ammonia has been absorbed, increases with respect to time and space. And on the right, you can see the mass fraction profiles. So in summary, this study shows the techno-economic feasibility of using the proposed absorbent enhanced ammonia synthesis for this solar thermochemical energy storage concept. The optimal design of the discharging loop or the heat recovery cycle was achieved using a detailed modeling of the process. And the nested optimization simulation approach that we applied here was able to account for the transient absorption into the design. And these are the metrics that we obtained for this particular optimal design. I would like to acknowledge the Solar Energy Technologies Office for its support, and thank you for your attention.